Have you ever looked at a huge bridge or a skyscraper and just wondered, how do they know it's going to hold? Well, engineers aren't just crossing their fingers. They're actually using this powerful language to talk to materials, to understand their limits, and to predict exactly how they'll behave. And that language, it's built on two key ideas: stress and strain. So today, let's learn how to speak it.
All right, here's our game plan. We're going to start with a simple, kind of idealized model that engineers use as their baseline. Then, we'll follow a material on its journey. As it gets pulled apart, we'll run into a weird little anomaly, and then we'll correct our model to match what's really going on. And finally, we'll see how all this stuff actually applies out there in the real world.
So to get started, we need a practical, reliable starting point. And in material science, that's what we call engineering stress and strain. You can think of it as the simplified model that we build pretty much everything else on top of.
First up, we've got engineering stress. It's a really straightforward but powerful idea. You just take the force, the load that you're putting on a material, and you divide it by the material's original undeformed cross-sectional area. Now, the key word here is original. It's something that's super easy to measure before you even start the test, which is exactly why it's the go-to starting point for most applications.
The other half of this conversation is engineering strain. So if stress is the force we're applying, strain is how the material decides to respond. It's basically just a measure of how much the object stretches or deforms, but relative to its original size. So for example, a strain of 100% just means the material has doubled in length. Simple as that.
So what happens when we take these two concepts and put them together? Well, we get a graph, and this graph tells the entire life story of a material as it's being pulled apart in what we call a tensile test. It's like a biography, but it's written in force and deformation.
Okay, as this story starts to unfold on the curve, the first thing you see is this perfectly straight line. This is called the elastic region. In this zone, stress and strain are perfectly proportional. The material is basically acting like a perfect spring. You pull it, it stretches. You let go, it snaps right back to its original shape. No harm, no foul.
But, any spring can be stretched too far. And that first critical point is the elastic limit. If you go past this point, the material is never going to be the same again. We've just entered the plastic deformation region, where the damage is permanent. The material yields. And as we keep pulling, the material actually gets stronger. That's called strain hardening, until it reaches its absolute peak strength. We call this the ultimate tensile strength, or UTS for short. This is the most engineering stress that material can possibly handle.
And right here, at its absolute strongest moment, something weird happens. Our material story has a plot twist. The curve, which has been climbing this whole time, suddenly, and kind of confusingly, starts to go down.
Okay, now hold on a second. This should make you pause. If the UTS is supposed to be the material's maximum strength, why in the world does the stress look like it's dropping? Is the material all of a sudden getting weaker right after it was at its strongest? That just doesn't feel right, does it?
Well, the answer isn't about the material's internal strength. It's actually about its external shape. The material isn't getting weaker at all. What's happening is that all the deformation starts to concentrate in one tiny spot, which begins to shrink really fast, and it forms what looks like a little neck. And so, we call this phenomenon necking.
And this is where our simple model falls apart. Remember how we calculated engineering stress? It was force divided by the original area. But with necking, the area where that force is actually being focused is now much, much smaller. Our whole foundational assumption just isn't true anymore. So to get an accurate picture of what's really going on inside that material while it's necking, we need to upgrade our tools. We need a model that can actually account for the material's changing shape, in real time. And this brings us to true stress and true strain. Now, instead of just relying on the original dimensions from the very beginning, these are calculated using the instantaneous area and length, the actual real dimensions of the specimen at any given moment during the test. It's like a running calculation that's constantly updating to reflect reality.
And here it is. This is the big aha moment. When we plot the true stress right on top of the same graph, we see a completely different story. That blue line, that's our old friend, the engineering curve. See how it peaks at the UTS and then drops off? But look at the red line. That's the true stress. It just keeps going up. There's no drop at all.
So here's the crucial takeaway. The material isn't getting weaker after it hits its peak strength. No way. In fact, it's actually getting stronger and stronger through strain hardening. It takes more and more force to keep deforming that shrinking, necking area all the way until it finally breaks. That whole downward slope we saw before, it was just an illusion, a trick created by our simplified model.
Whew. Okay,
So we've gone on quite a journey here, from a simple, really practical model to one that's a bit more complex, but a whole lot more accurate. So let's just recap how all these ideas fit together in the real world of engineering.
We started with our baseline, engineering stress and strain, that idealized model that works great for the elastic part of the journey. Then we hit a reality check. Things like necking showed us where that model breaks down. This led us to the correction, using true stress and strain to understand the material's actual behavior all the way to fracture. And mastering all of these concepts is what allows engineers to analyze the incredibly complex forces happening on real-world structures.
Which kind of leaves us with one last thought. We've spent all this time looking at what happens when you just pull on a simple bar of material. But, the world isn't made of simple bars getting pulled in one direction. So the real question is, how do these fundamental principles all combine and interact to handle the complex pushes, pulls, and twists that keep the amazing structures all around us standing strong and safe every single day?